More than 2,000 years ago, the great mathematician Archimedes said, "Give me a place to stand on, and I will move the earth." What Archimedes had discovered is what we now call mechanical advantage. Mathematically, you can show it as the ratio of the output force to the input force. And the tool or machine that Archimedes was referring to is called the lever. The lever is a bar or a board that you set on a fixed point called the fulcrum, and you use it as a pivot. So in this diagram, if the man pushes down, the rock will move up. If you place the pivot or fulcrum close to the load, to the thing that's being lifted, which we're calling the output force, then you'll find that it requires a relatively small input force. However, you may also notice that the output goes only a very short distance, whereas the input has to move a much longer distance. So a small input force exerted through a large distance can produce a large output force over a short distance, and in this way, the lever can multiply the input force. In other words, it can have a mechanical advantage. However, this almost seems too good to be true. A small force somehow put in results in a large force output. It's like you're almost getting something for nothing. Now, earlier in the course, I'm sure you learned about the principle of conservation of energy. So there's no way that a machine such as this lever could multiply energy. Let's take a closer look at what's going on mathematically. What we would find is that if you take both of our observations, the force input and output, and the distance that you have to move versus the distance that the load moves, if you multiply force times distance on the left, multiply force times distance on the right, those two products will be equal to each other. Now, force times distance may sound familiar to you. Have you ever seen an equation that had force times distance in it? That's the equation for work. Work, in physics terms, is an applied force moving an object. So, essentially, what you can show for this lever system is that the work input is equal to the work output. Force times distance on one side equals force times distance on the other side. Here's an example of a lever being used by a child. The child is pushing down with a 10 Newton input force, and she is lifting an 80 Newton rock. So that's our output force. But the child has to push 1 meter downwards in order to lift the rock 1/8 of a meter, or about 0.125 meters upwards. If you put this into equation form, the force and distance on the left should equal the force and distance on the right. Looking at the numbers, we in fact get 10 newtons times 1 meter equals 80 newtons times 0.125 meters. And if you check, 10 times 1 does in fact equal 80 times 0.125. But what are the units of work? Well, we see that work is force times distance. In the metric system, we measure force in newtons. Distance is measured in meters. So the unit of work would be the Newton meter. But you may recall that 1 Newton meter has another name. We call it the joule. Aren't joules the unit for energy? They are indeed. What you've just discovered is that work and energy are actually the same thing. Now we know that no energy is created or destroyed by any system. Energy can change form, but the total amount of energy, at least in the entire universe, does not change. And therefore, our lever has to obey the law of conservation of energy. We could substitute, instead of work in equals work out, the words energy. Energy in on the left side must equal energy out on the right side. So a machine, such as the lever, transfers energy from one place to another, or it can transform it from one form to another. In the case of simple machines like the lever, we can also say that the function of a machine is to change the size and or direction of an input force. Change either the size or the direction of an input force and you've got a machine. But the concept that underlies every machine is the conservation of energy. A machine cannot put out more energy than is put into it. No matter where you hear that claim, on the internet or on television, you don't get something for nothing. Now if you look again at the equation, work input equals work output, that's what you might call an ideal or theoretical situation. In real life, there's always going to be a little bit of friction involved, and so you're going to lose a little bit of energy from the system as heat energy. It's not lost from the universe, but it will be lost as far as being useful to you. But if we go back to our equation form, force times distance on the input side equaling force times distance on the output side, and if we take that equation now and rearrange it a little bit, you find out something interesting. Since this is an equation, the left side equals the right side. If we do the same manipulation on the left and right, then that should be okay. So let's gather up the forces on the left and the distances on the right by doing a little division, cross multiplication, and you would come up with this equation right here. Force in over force out equals distance out over distance in. It's the same equation as above, it's just rearranged to show a ratio. But wait, do you recall that in an earlier slide we saw force in over force out? We gave that a name. We called it mechanical advantage. That's what Archimedes discovered. Now we're seeing that you can actually measure mechanical advantage by using the distances. If you measure how far the output moves, divided by how far you had to move on the input side, that will also give you the mechanical advantage. But in real life, as I said earlier, you're going to have to actually expend a little more force than you might expect due to things like friction. So the left side, we actually term the actual mechanical advantage, and the right we call the ideal mechanical advantage or theoretical mechanical advantage. Sometimes we abbreviate it the IMA. So on the right, distance out over distance in, we're going to call that the ideal mechanical advantage. On the left, we're going to call that the actual mechanical advantage, or AMA. Now, in the simple pulley system that you're going to experiment with today, these two should be very, very close to each other. But in more complex or compound machines, where you're going to have a great deal of friction, you'll find a bigger difference between these two measurements. So I've mentioned this term machine or simple machine several times. You can think of all kinds of machines in our world. They change energy, either type or they transform a force or the direction of a force. In classical physics, we say there are 6 simple machines, including the lever, the pulley, the wheel and axle, the inclined plane, the wedge, and the screw. Now, in practice, in modern times, we recognize there are actually many more simple machines or machine parts, but these are the 6 types that we typically study in a Physics 1 course. So we're going to look at the pulley today. Pulley is simply a wheel that's sitting on an axle so it can turn, and you put some sort of rope or string or wire over it, One end will be attached to a load and the other end will be attached to whatever is pulling on the load, which in your case is going to be your muscles. We want you to try 3 different pulley systems today. First, we'll have what's called a single fixed pulley. If you pull on the rope, the load will move up while you pull down. Since it's just a single strand over a single fixed point here, essentially whatever this block or load weighs, that's how much force you're going to have to use to lift it. So why would you even want to use that if it doesn't supply you with a mechanical advantage, reducing the input force? Well, in this case, what you get is a change in direction. It turns out that for the human body, it's generally easier to pull down than it is to lift up. You have larger bicep muscles, and you're built in order to stand, to pull down. Whereas if you lift it up, you're going to be using your triceps and your back. You're liable to throw your back out if you lift something the wrong way. So we might use a single fixed pulley to change the direction of a force. But pulleys don't have to be fixed in place. You can have what's known as a movable pulley. In this case, we've got one single movable pulley. We have to pull up. The load also goes up, so the direction is the same, but you'll actually find a mechanical advantage in this situation. You'll find that it's actually easier in terms of the amount of force on your body to lift the load using this pulley system. So I want you to try that today. And then we're going to try a third system called a compound pulley, or sometimes people refer to it as a block and tackle. We're going to have a single fixed pulley and a single movable pulley. Again, you should notice a mechanical advantage, but you will also notice, because of this fixed pulley up here, you'll notice a direction change. You pull down, the load goes up. As an example, you might pull down with 1 Newton of force to lift a 2 Newton load. We would say that that system has a mechanical advantage of 2. The output force is always what you're lifting. The input force is how much effort you have to put into it. 2 newtons divided by 1 Newton equals 2. You'll notice there are no units. Mechanical advantage is a rating system. It tells you how much the system will multiply your force. Now, earlier I showed you 2 ways of calculating mechanical advantage. With a pulley system, we have another way of calculating the ideal mechanical advantage, and that's to count the number of strands of rope that are actually supporting the load. So in this little picture shown here, 2 of the strands, this one and this one, are actually picking up this load here. You don't count the rope that you pull down with. That one's not supporting the load, although of course it is a necessary part of the system. But because there are 2 strands of rope supporting the load, we expect this particular pulley system to have a mechanical advantage of 2. That's the ideal mechanical advantage. You can use this same rope strand counting method to find the ideal mechanical advantage of any pulley system. In this first system here, only 1 strand of rope is actually supporting the load. The other strand attached to your hand to the spring scale, we're not going to count that, so that's going to have a mechanical advantage of 1. This system, this time the spring is being pulled up, and so it supports the load up. We're going to count that. So there are 2 strands of rope. We're going to call that a mechanical advantage of 2. Again, 2 strands of rope supporting the load. The one pulling down doesn't count. That's a mechanical advantage of 2. And what about this more complex system? Well, we see 1, 2, 3, 4 strands of rope supporting the load. The one pulling down doesn't count, so even though there are 5 strands of rope, only 4 support the load. We should see a mechanical advantage of 4. What that means is if you put 25 newtons of force in, you could lift a 100 Newton 4 times more force, ideally. But ideally is one situation. The real world, we have a different situation. We have friction. You're going to lose some of your force due to friction involved in the system. So another calculation that you can make with machines is called your efficiency. You can find out how much that friction is affecting you. Efficiency can be calculated in two ways. It's the work output divided by the work input, and we usually do express it as a percent, so you multiply this ratio by 100. No real machine can be 100% efficient or over 100% efficient. If you do efficiency calculation and you get an answer greater than 100, you need to start over. Another way that you can calculate efficiency is by using the mechanical advantage. You'll get the same answer. The actual mechanical advantage divided by the ideal mechanical advantage will also give you the efficiency. If you multiply by 100, you can change it into a percent. Again, it should be less than 100%. In today's lab, we're going to use some little plastic pulleys. They've got these hooks on them so you can conveniently hook on the load or a spring scale or a string. And we want you to try 3 different situations. Now the spring scale, it's going to have 2 sides on it. It's going to have a little lever. When you pull down on this hook down here, the lever will move down. Read the side that says newtons. We want forces. Your lab sheet says mass, but that is incorrect. You always measure the force in a mechanical system in order to calculate the amount of work. So in figure A here, you're going to lift a weight with a single fixed pulley. What you do is you look at the contact points of the rope and the pulley and set it up accordingly. So it looks like you're going to want to fix the pulley by hooking it to you'll have crossbars. So fix it to one of the crossbars, then tie the rope to one end of the weight, push it through the upper part of the pulley, and hook the other end to the spring scale. That's a single fixed pulley. Test that out, find its mechanical advantage, its efficiency, and anything else that you might want to note. Then you're going to try a single movable pulley. This time we tie the string to the crossbar, push it through the bottom of the pulley, hook the weight on, and then tie the other end of the string to the spring scale. It's important to keep this weight on the pulley. If you let the tension off, the rope will come slipping off of the pulley and you'll have to set it up again. And then the third system, a compound pulley, you're going to use one single pulley at the top that is fixed, one movable pulley at the bottom. Now, the pulleys that you get, you may actually have a double pulley, such as the one shown in the upper left-hand corner of the screen. Only use to lower the larger pulley for this system. Just ignore the fact that you have that other pulley up at the top. But you want to fix that to the crossbar, tie the string to the bottom of the fixed pulley, push it through the bottom of the movable pulley, flip it through the top of the fixed pulley, and then tie it to the spring scale. Just follow the string in the diagram and you should be able to set it up. Test all 3 of those, write your mechanical advantages, and find out what differences also in direction each of these systems applies. And so please gather up in a group. I know Mr. Wright usually counts you off, but we may have to find a different way to put you in a group today. I think there are 6 setups, so you have to divide up into groups of 4 or 5 each, and space is kind of limited, so just be nice to each other. And let's go to lab. By the way, you do have a number of equations. You have an equation sheet somewhere. It won't look exactly like this, but you are dealing with a number of equations today. Try not to get too confused. The reason why we're having you practice this is so you get familiar with these equations. And let me also just leave you with this thought. What will you use as a lever to move the world?